Well, good evening and welcome to Kopernik Observatory's FNL Friday night live stream. My name is Drew Desker. I'm the director of the Kopernik Observatory. It's great to have you with us this evening. Got a nice crew already of 18 plus users, or viewers. And so anyway, I hope you're well. I hope you have a mask with you. I'll be putting mine on in a few minutes when our presenter talks. But people have been asking, when will Kopernik open again? And unfortunately, we're just in a situation that it is just not safe to gather in public, especially here in Broome County. Unfortunately, the numbers for COVID diagnoses have really spiked recently, and so we're just asking people to stay home and do what you're doing tonight. Participating in a Kopernik program from the comfort of your own home. And now, for those of you who may be watching for the first time or relatively new, again, we can't really charge. We don't charge for these live streams. But if you actually look down in the description below on the YouTube channel, if you there's an opportunity for you to donate. So if you're in a position financially to offer some support, that would really be helpful to us. We're really doing our best to try and keep these going, but again, we have to pay for the electricity and everything else. So if you're in a position to help us out, that'd be great. So tonight's talk will be about engineering, and specifically aerospace engineering. But then also, because as it turns out, this evening we've got a fairly nice clear sky. Jeremy Carty, the Kopernik's live stream astronomer, will be starting up another program right after this finishes, probably close to 9 o'clock or so. It'll be a different URL, and I'll put that in the chat window. So when you, if you want to stick around for that, we just a couple days ago passed the close approach of Mars, and so Mars is about as close as we'll see in 26 months. It's now just starting to slowly move away. I also understand that the Elon Musk's Spaceman is just rounding about Mars right now. Unfortunately, we won't be seeing Spaceman through the telescopes tonight, but we just know that he's out there. And then in a couple weeks, a couple Saturdays from now, on October 23rd, we'll be doing our Kopernik Astrofest. I believe this will be our 30th year of Astrofest, and this one, as everything else these days, will be virtual. But we've got a bunch of great speakers. We'll have some stuff throughout the afternoon and into the evening, so you can plug in, and unplug as your schedule permits. We just this evening was able to secure Nagi Cox, who is a systems engineer from the Jet Propulsion Laboratory, will be our keynote speaker on that Saturday evening. But anyway, let's get into tonight's program. I personally, there's probably no surprise that when we're booking, trying to find the speakers, very often I end up looking for speakers that I find interesting, quite frankly. And I was actually trained as an engineer, and so when David said, "Hey, I have an opportunity to talk about how engineers do some problem solving, around the space shuttle," I said, "Absolutely, let's sign you up for a talk." It was originally supposed to be earlier this spring, but with the pandemic, we figured we just wait a little bit to see if we could eke it out in person. Clearly, that's not going to happen anytime soon. So we instead are just moving to an all virtual format. So at this point, I'm going to put my mask on and introduce David Woods, and I'll let him introduce himself, and then we'll dive into the program.
I click on the image to.
No, yeah, just you can introduce yourself here.
Click on this.
Yep. And hold on. Actually, go back one.
Yeah.
And yep. Okay.
Okay. Well, good evening. My name is David Woods. I'm a retired IBM Lockheed Martin Aerospace Systems engineer. And I was going to use tonight's program to show you how engineers use both unclassified and classified information sources to solve some very interesting and complicated engineering problems. And I will end with an example of the Space Shuttle Discovery's launch Abort on its first mission attempt. You will see how engineers research a problem, and in this case, how they found a surprising solution and surprising source and solution to allow them for it to go on to be the most successful of all the space shuttles. So engineers are problem solvers. Engineers are problem solvers by gathering information for a particular project and then use that information to see a program through to completion. And as a youngster, I was always fascinated with space exploration, so I wanted a career in a related engineering field. I have an interesting letter that I received back when I was in high school from a gentleman named Werner von Braun. He was responding to some questions that I had about a book that he had written called The Mars Project. The main name may sound familiar because he's a NASA engineering program manager, the chief architect of the Saturn V launch vehicle for the United States Apollo manned lunar program. The Soviet Union also had a similar program, and it was run by a gentleman called Vasily Mishin, and I had an opportunity to meet him as well. And you can see me with him, and the bottom picture there is him autographing a presentation that he gave. The conference that we attended had an evening session for the attendees at the National Air and Space Museum in Washington. And Mission arrived alone, so I motioned him to follow me down to the end of the building where we had an Apollo lunar module. And I used his camera to take some pictures for him of him standing in front of it, and then I took some pictures for myself. No one else seemed to realize who he was, so this is kind of unique. The head of the Soviet manned lunar program in front of an Apollo lunar module. Quite a unique picture. I've always been interested in space programs, especially the Soviet program, and these are a series of technical illustrations that I did as part of a presentation for the Science Policy Research Division of the U.S. Library of Congress back in the 80s. And as an engineer, my question was always, what do things look like and how do they work? So after college, I accepted an engineering position at the IBM Space Guidance Center in Owego, which was at the height of the Cold War when we were worried about possible conflict with the Soviet Union. At the time, we wanted to know what we were up against, what sorts of military systems they had, how many they had, where they were deployed. One way to find out was to obtain detailed reconnaissance photographs of these targets and their installations. Now, photographing a target from Earth orbit is extremely difficult. The target will be at least 200 miles away if directly above it. Spacecraft will be traveling at 5 miles per second. To get any details, the magnification has to be so high that an individual photograph will be less than a mile on a side. It would be like trying to photograph the Washington Monument from Binghamton while traveling on Route 17 at 5 miles per second. And unless there is some sort of compensation, the image will be just a blur as the target goes by. So when I joined, IBM was working on the Image Velocity Sensor Subsystem, a program that has since been declassified, so I can talk a little bit about it. The IVSS was going to be used on the U.S. Air Force Manned Orbiting Laboratory to steer the camera system's field of view to targets of interest so the images would not be blurred. And this is, you can see what the vehicle would look like. They would launch a Gemini spacecraft on top of a Titan III. Once in orbit, the two astronauts would open up a hatch through the heat shield, travel through a tunnel into a living compartment, and then control the optical system to take pictures of targets of interest. Now, as I indicated, this was a very highly classified program, and people might say, well, what do you mean by classified? Well, there's different levels of information, and these are different levels of classification for them. A weather forecast coming out of the government is unclassified. There's no reason to have any restrictions on it. There is confidential. Say somebody was at a embassy reception and he overheard some little choice bit of information and wants to pass it on to his people. That would be something that we would like to know that, or within our own group, that we know about it and not pass along the fact that we know that information. Secret information is what is really serious, and we definitely want to treat that and not disclose it to the general public. The most highly classified of information is top secret, sensitive, compartmentalized information. And it is so top secret that it is only released to specific people with a specific need to know. Now, for some of the younger people in our audience, you might say, well, can you give me an example of what this would be like? Well, let's give you an example. Let's imagine that a princess has been kidnapped by an evil king, and she is being held for ransom at his far-off castle. The prince is gathering information to plan a rescue mission, and here is the information he has found. He has unclassified information. He knows where the castle is, what it looks like from the outside. He has some confidential information because there are people who have been inside and they know a little bit about what it looks inside there. He has some secret information because he knows where the secret gates are so that he can get into the castle. And then he has some top secret information because he has a spy inside the castle who can lead him to the princess, so he has to protect the spy and only tell those individuals with a specific need to know. You might say, well, okay, that's all well and interesting, but in my line of work, I will never have an opportunity to see or deal with classified information. So how would you like to see some actual top secret, sensitive, compartmentalized information? Let me give you a little bit of background information. In 1957, the Soviets started testing their giant SS-6 ICBM, SS meaning surface to surface. After achieving 2 successful long-range tests, they used to put the first satellite into orbit, Sputnik 1. Sputnik 3 the following spring used the same launch vehicle, and it weighed nearly 3,000 pounds. So long-range photographs from the ground of the final stage showed that it was nearly 72 feet long, so it was huge, meaning that it could easily send a nuclear warhead all the way to the United States. So the SS-6 was a threat, and we wanted to know everything about it, including where the launch sites were, how many of these missiles there were, and so on. At the time, we were using CIA U-2 aircraft to fly out of Pakistan to venture into the Soviet Union. And eventually they found the launch site, which was just north of a train stop on the railroad line between Moscow and Tashkent. The CIA used an old Nazi German Wehrmacht mapping document called from World War II that showed the name of the train stop to be called Tyra Tam. A small city had grown up there for the workers, so they used that for the name of the range, even though the launch facility was at the end of that long road going north. So the launch facility was called the Tyra Tam Missile Test Center. Now here's an example of a modern day classified information from 1963 that was top secret, sensitive, compartmentalized information before it was classified in the year 2002. The picture on the right with the red border shows that it was called Top Secret Rough, and it is a drawing of the launch complex at Tyra Tam. The information was part of the Talent Keyhole, KH program. So this information was TS, top secret, SCI, specially compartmentalized information, TK, Talent Keyhole. The name came from spying, like peeking through a keyhole in the sky, in this case using aircraft and satellites from above. And this is a map that was developed from spy aircraft and satellite photographs of the Soviet SS-6 launch pad, where the first satellites and the first cosmonauts were launched into Earth orbit. And only people with a top secret clearance and a need to know had access to this imagery under the Talent Keyhole overhead imagery program, and were allowed to see this sort of information. The word rough, it was relegated for imagery. Another label was called ZARF, which was for intercepted radio signals. There were a whole series of categories because only information was released only on a need-to-know basis. Once the photographs had been attained, you had to figure out what you were looking at, so they had to be interpreted. And here's an example of a declassified analysis of satellite photos of the facilities where the giant Soviet SS N-1 rocket was being tested. The blacked out areas called redactions are those that are still classified, like the dates and the precision of the location. You know, it gives degrees and minutes, but the actual seconds of location is just too accurate and it's still classified. Each of the 4 launch attempts of the giant N-1 failed, and their manned lunar landing program was eventually canceled. And here you can see a picture of one of them as it's disintegrating during a launch. So the Soviets built a small city for workers south of Tyuratam and called that city Leninsk. You might be wondering why the Cosmodrome is called Baikonur if the original village was called Tyuratam and the workers' city was called Leninsk. When Yuri Gagarin made the first human space flight, he was the first human to orbit the Earth. The Soviets wanted to register that accomplishment with the French Fédération Astronautique Internationale. And one of the requirements was to state where the flight had started. And they certainly didn't want to acknowledge the location of the Cosmodrome, so they picked a small mining village several hundred miles downrange, a village called Baikonur. So from that point on, the name of the center for the Russians has been called the Baikonur Cosmodrome, even though Tyuratam and Leninsk are still on the map. The U-2 flights over Russia were ended in 1960 when one of them made a flight out of Pakistan over Tyuratam before it was shot down over Sverdlovsk on its way to Norway. And from that point on, we had to rely on unmanned satellites taking photographs from orbit and returning the film in small capsules. Because they were cheaper than the Manned Orbiting Laboratory, MOL, with its IVSS, that program was canceled and no launches were ever conducted. The first Corona KH-1 satellites carried a single film return capsule, and later satellites carried more capsules. Finally, the huge KH-9 hexagon satellite carried 4 capsules, and you can see a picture of the hexagon system. It was mammoth. The results that they got were very good, but they had the disadvantage of not being able to see what they had photographed until the capsule was returned. And also they used up a good capsule early if pictures were needed right away. So we've come a long way from the 1960s when we needed astronauts and photographic film to conduct surveillance of foreign threats. Today, engineers have made tremendous advances with computers and electronic performance. Just take a look at this 1956 metric ton IBM 306 RAMEC 5 megabyte hard drive being loaded into a propeller-driven Pan Am cargo aircraft. Compare that with a simple 16 gigabyte thumb drive today that you can easily purchase for use in your personal home computer. And today we no longer rely on photographic film, which can take days between when pictures are taken and then they are available for analysis. Instead, we use charge-coupled devices and digital cameras that are available to everyone that produce pictures that can be instantaneously sent around the world over the internet. So all of this is thanks to the hard work, problem-solving engineers. Today we have commercial satellites that can take unclassified digital pictures from Baikonur from above, like Google Earth. Western people can even go there to watch an unclassified Soyuz launch of American and European astronauts and Russian cosmonauts to the International Space Station. I've been to Baikonur twice, once to watch a manned launch. And if you take a look at that center picture, that's a picture of me on the launch pad with the gantry in the background. So engineers are problem solvers who get to work on a lot of interesting programs. I'd like to give you an example of an engineering problem that developed on one of the space shuttles, how it was discovered, and how it was fixed. I only learned about it a few years ago in another area at the Owego facility. It is one that I was not personally involved in. It is completely unclassified, so I can tell you everything about it. First, let's describe the Space Shuttle and how it would conduct a mission. The Space Shuttle was designed to carry up to 7 people plus cargo into Earth orbit. Early missions were used to transport satellites and probes into low Earth orbit. Later missions were used to build the International Space Station. The Space Shuttle was retired in 2011 after completing 135 missions. The Space Shuttle itself consisted of a winged flyback orbiter with a crew cabin forward and a cargo bay aft. At its base were 3 liquid propellant engines. They drew liquid oxygen and liquid hydrogen propellant from a large attached external tank, and attached to the external tank were 2 solid rocket boosters. 5 space shuttles were built. 2 of them were lost. The remaining 3 have been retired and are now in museums on permanent display. A launch sequence would begin with a stream of igniters spraying sparks, a shower of sparks in front of the 3 main liquid oxygen, liquid hydrogen engines. Once ignited, the exhaust was primarily in the infrared regions, so there was very little visible flame from them. And if you take a look at the first 2 pictures, the middle picture especially, you can see there's very little flame that you see there. Once they had ignited and were up to full thrust, the 2 solid propellant strap-on boosters could be safely ignited, giving the system full thrust. The burning solid propellant from the strap-on exhaust was very visible. You can see the difference between the 2 on the right. The Space Shuttle could then safely lift off from the launch pad and proceed on into Earth orbit. The Space Shuttle released its solid boosters when they were used up about 2 minutes into the flight. They used parachutes to land in the ocean where they could be recovered, towed back, cleaned out, and reused on future missions. Before reaching Earth orbit, the external tank was empty and was released to fall back into the Earth's atmosphere and burn up over the Indian Ocean. The Space Shuttle would then use its small maneuvering engines to propel it on into Earth orbit with its cargo. Once in orbit, the shuttle would release a satellite from its cargo bay, like the Hubble Space Telescope that you see here, or it could dock with the International Space Station to bring up new modules to build the station or cargo to support the crews and work they were performing. STS-12, Space Transportation System number 12, was the 12th Space Shuttle mission and the first one for the Space Shuttle Discovery. It had a 6-member crew. Its cargo consisted of 3 separate satellites plus a large array that was going to be extended and then retrieved before coming back to Earth. The launch process for Space Shuttle Discovery began on 26 June 1984 as Space Transportation System STS-12. The countdown proceeded normally with main engine ignition. Then, just before the solid rocket boosters were ignited at T-minus 4 seconds, the engines were shut down. There had been a launch abort. Here's some of the commentary that went on as a result of that. It says, "We have an abort by the onboard computers. We do not show engine start on number 1. We have red lights on 2 and 3 in the cockpit, but not 1. In other words, engines number 2 and 3 were shut down, but not engine number 1, even though it did not ignite. 2 of the 3 main engines had ignited, but the 3rd one had not. The crew could immediately have evacuated, but Hartsfield, who was the mission commander, elected to sit tight. Unknown to the crew, hydrogen venting from the failed engine was burning, causing a nearly invisible fire at the base of the vehicle and up the side where the crew hatch was, with the 6 astronauts still on board. Because the fire was invisible to human eyes, had the astronauts used the normal emergency escape procedure across the service arm to the slide wire escape baskets, they would have run right into the fire. So this was potentially a very dangerous situation. When they finally did emerge, they were drenched with water from the fire suppression system, and the entire gantry was soaked with the white room ankle deep in water. Fortunately, there were no injuries or damage, and the flame was quickly put out. And here you can see what the procedure is. There is a service arm attached to the shuttle. The astronauts would quickly get into the escape route, climb over to a series of escape baskets, and use a zip wire that would allow them to pass down to the ground safely away from the shuttle itself. It was later determined that irregular slow operation of the main hydrogen valve in a Space Shuttle engine main number 3 had resulted in the engine shutdown, and the launch was aborted. As a result, a decision was made to roll Discovery back to the vehicle assembly building to remove and replace the engine. Because of the delay, the mission was combined, its payload, with another planned mission to allow the program to remain on schedule. But what most people don't realize is that this was the second launch attempt of Discovery. This first attempt had occurred the day before, and it was suspended at the T-minus 32-minute mark when 2 memory parity errors occurred in the general purpose computer number 5 that ran the backup flight system software. Launch was scrubbed for the day at the T-minus 20 minutes mark so the computer could be removed and replaced, and another launch attempt made the next day. It was later discovered that under worst-case timing conditions that the master event controller would not process certain critical event commands in the proper time intervals. As a result, this could have prevented the separation of the solid rocket boosters and the external tank, as well as other vital operations. All of that was fixed with a software patch that was developed, tested, and incorporated for launch the next day. So one of the onboard computers that had failed that caused the launch attempt to be scrubbed and aborted. The space shuttle was secured and the crew was made a safe exit. The Space Shuttle uses 5 AP101 computers as main purpose computers. They were built at the IBM Owego, New York facility. 4 operated in sync for redundancy. The 5th one was the backup flight system computer, and it was the 5th computer that had caused the launch scrub. The computer that failed had worked fine for over 900 hours of testing before the failure. And here you can see a picture of what an AP101 computer looks like. We actually have another one that's been donated that is in the lobby of the Kopernik Observatory. So if you want to get a chance to see it, when we open for visits again, you'll have an opportunity to do that.
Actually, if I could I just grab it briefly here? I'm gonna
by all means
go to the webcam, and this is, give me a second here to flip around. So this is actually one of those computers that David was mentioning that we actually have here at Kopernik that were built here in Owego.
That's correct.
So it's interesting, actually. There's some Lockheed Martin engineers that come in and they'll look at some of the markings on here and says, "Oh, I know where that bay is. I know in that building." So it's a great thing that we have such a extended
local community
a local connection. So anyway, let me get you back to your program, and there you go.
So again, this is what an AP101 general purpose computer looks like. It has a series of pages inside, and on each of the pages are a series of little computer modules. And the problem was isolated down to AP101 computer number 5, and then to a specific page in the computer, and then to a specific module on that page. The computer modules are sealed units with external contact pins. Internally, there is a chip with a massive number of printed circuits that perform the required functions for its mission. These pictures are not of the AP101 faulty chip, but they are representative of its general construction. On the picture on the left, you can see a series of contact points with some wires leading off from the computer chip itself. Pictures on the right show those little wires going over to contact points on the printed circuit page where the module is located. Here's another picture. Again, it's not of the AP101, but it's representative. Once the printed circuit chip has been bonded to its circuit board, Tiny wires are then bonded from points on the chip over to contact points on the circuit board. The faulty computer chip module was removed from the board and opened for examination, and these are pictures of the actual chip. Under an electron microscope, it could clearly be seen that there was contamination spots on the upper right-hand corner of the chip. These were very expensive chips, and they were supposed to be manufactured in super clean facilities. So the engineers asked, what was the contamination and how did it get there? These are some more pictures below that are from a totally different but similar chip obtained at the U.S. Air Force Rome Air Development Center in Rome, New York, that had similar contamination problems. Note that within the contamination region there are tiny crystals, some that are almost the same dimension as the chip circuit paths. An analysis of the different contamination crystals on the AP101 chip showed that to be potassium chloride with a residue of tobacco nicotine. Something had laid down a spot on that material with this material in it. The chip was heated, dried as part of the manufacturing process, and that formed the crystals, and then it was coated with a sealant. Unfortunately, the sealant could hold moisture, and it would slowly soak into the crystals, causing them to eventually become chemically active and begin eating into the printed circuit patterns or the wire bonding contacts. So the computer chips were supposed to be manufactured in a super clean room facilities. Where did the potassium chloride come from? The most likely source was from someone who had violated the clean room requirements and had sneezed with his or her face mask off. A droplet of spittle from the sneeze had landed on the chip as it was being manufactured. Corrosion slowly ate away at one of the wire contacts so that it eventually broke and caused the computer to fail and scrub the launch attempt. And today we have much better quality control measures. You can see in the picture in the upper left, the young lady has just a little circular plastic face shield in front of her, no face mask. She's wearing gloves, but the gown that she's wearing, the sleeves are open, and the possibility of contamination there. And as you can see, when somebody sneezes, it sends out a spray of droplets, and one of these landed on that computer chip module. Today we have much better quality control. The people wear complete facial masks, gloves, and the cuffs are completely taped shut so that there's no possibility of contamination there. So there were numerous problems that had occurred that could have had disastrous consequences. The worst case would have been where, had the AP101 failure not occurred until after launch had occurred, if that main engine then shut down, the system would not have been up to full thrust, meaning that it could never have reached Earth orbit. And finally, if those software problems had not been discovered and fixed, there's the possibility that separation of the solid rocket boosters and the external tank might not have occurred, preventing the shuttle from performing a return to launch site abort. As a result, Space Shuttle Discovery and its crew could have been lost. Fortunately, none of that happened. So the first launch attempt of Space Shuttle Discovery was interrupted by someone who had coughed or sneezed and generated drops of human spittle that landed on a critical circuit path in a computer chip module on a computer page in one of the onboard AP101 computers. This was after 900 hours of flawless computer operations without any problems. The more serious launch abort occurred the next day, just 4 seconds before launch, when one of the 3 main engines failed to fire up. For the AP101 contamination, it would ultimately cost engineers $500,000 to remove and replace the defective computer and conduct the failure analysis. And it took $10 million to turn Space Shuttle Discovery around for a successful launch on mission STS-12 nearly 3 months later, on the 30th of August, 1984. All of these all of this recovery was made possible by problem-solving engineers. I had the pleasure of seeing Space Shuttle Discovery twice. The first time was in April 1965 when I took my 3 children to watch Discovery's second launch, STS-16, where it carried 3 astronauts and launched 2 communication satellites into Earth orbit. The second time that I saw it was in 1984 when I took my grandson Alex and his uncle Steve to the Smithsonian Air and Space Museum in Virginia, which is now the permanent home of Space Shuttle Discovery. It had operated from STS-12 until its final landing at the end of STS-133 in 2011. Discovery had survived the problems from the first launch attempt and gone on to fly more than any other spacecraft, having completed 39 successful missions in over 27 years of service. And here you can get an idea of just how big it is. The picture on the right shows my grandson underneath it, underneath the back end of Space Shuttle Discovery. It was a huge machine. So these are examples of the sorts of amazing things that engineers do. Engineers are problem solvers. They work to make things better, faster, smaller, lighter, cheaper, and then correct things when they don't work as they should. This is the picture of the crews from 2 Soyuz spacecraft, each one carrying 3 members, and a space shuttle mission carrying 7. So all of them on board the International Space Station. These are men and women from different nationalities, different ethnic backgrounds. It shows that if you work hard, get a good education, you too can become anything that you want to. So consider engineering to reach for the stars and follow your dreams.
Hi, I'm Expedition 24 Flight Engineer Tracy Caldwell Dyson on board the International Space Station, 220 miles above the Earth. Many of us were captivated by the Apollo moon landings and other amazing experiences that inspired us to become astronauts. Each of us carried that dream all the way through school. And guess what? Studying science, technology, engineering, and math can help you realize your own dream. This summer will be special for you. NASA wants to invite you to become involved with NASA's Summer of Innovation. We want to give you an extra boost to help you learn more about science and technology as you prepare for your careers. So join us at NASA in finding out all the exciting things that math, science, and engineering can do in our world and in space. Imagine it, explore it, do it. Who knows what you'll discover?
Well, thank you. That ends this evening's program. I'll turn it back over to Drew at this point.
All right. Well, David, I think you did a great job explaining everything. There are no questions. So,
Okay.
So that is great. Yeah, again, I think one of the nice things about living here in this area, not only because of Kopernik, but again, the history of this area and its connection to the space program. And it's not only just IBM Federal Systems, but also Link simulators were critical to the success of the Apollo missions. I'm actually reading Michael Collins's book of his, and I'm blanking the title at the moment, but it's a great thing, and one of the things that the astronauts really do rely on were those simulators. So anyway, at some point we hope to have you again back up here to for our programs in person. We do have a couple of other live streams that are coming up. In a moment, I'm going to be sending in the chat window right around 9 o'clock, so you have an opportunity to do a little bit of a bio break, maybe refresh your drink or whatever it is that you're consuming at the moment. And at 9 o'clock, Jeremy Cardy will do a live stream observing session using our 6-inch telescope. Again, we just went through the opposition of Mars, where Mars was the close approach of Mars, so that he'll get an opportunity to take a look at Mars, but also Jupiter and Saturn are out there right now. As I said, also later on, we've got on 2 Saturdays from now, we'll be doing our Astrofest, and so that'll be an afternoon into the evening program. So be a number of number of presentations for you to check in on, and then the Friday after that, October 30th. Phil Cooper, who has done a couple of programs up here about the Apollo program, he did one on Apollo 11 and Apollo 12, will actually be talking about Apollo 13 and how it was a successful failure. Phil does a great job with this presentation, so that's definitely not one to miss. And then 2 weeks after that, he'll do a wrap-up of the remaining Apollo missions, Apollo 14 through 17. And that'll be, I think, on the 9th of November, whatever 2 Fridays after that. So we'll have a couple of other programs coming up. We'll continue to do these live streams as often as we can. And it's great to have you. Thank you, Michael. It's Michael Collins' book. It's called Carrying the Fire. That's my wife, because it's on my bedstand. So it's what I read every night before I go to bed. So anyway, I hope you found this program interesting. Again, engineering is, I went into it as a profession, and I just, even though I've sort of morphed into becoming the director here at Kopernik, I always, one of my hobbies is ham radio, and there's all sorts of ways that you can play as an engineer with ham radio. We've actually had our students talk to astronauts on the International Space Station, and through ham radio. So if you want to learn more about ham radio, reach out to me at Kopernik's website. David, you had something you wanted to?
Well, you could talk about what membership.
Oh yes. Okay, so let's also do a little bit of self-promotion. Again, if you enjoyed this evening's presentation, please look down in the description area just below with this image here, the video image, and there's an opportunity for you to donate. Another way to stay engaged with Kopernik is actually to become a member. Kopernik, again, we don't get any government funding whatsoever, and so it's through programs like this, through memberships. We do get some grants for some programs, but at this point, those right now are really sort of on hold. And so becoming a Kopernik member is actually a great way to support us, but also it's a great thing in that we belong to what's called the Association of Science and Technology Centers. It's a consortium of over 350 other science centers. So with your Kopernik membership, you can get into those 350 other science centers for free. So you could go down to the Franklin Institute in Philadelphia, or the Intrepid Museum down in New York City, which actually has the Enterprise, which is the one space shuttle that actually was built but never actually went to space. It was actually used for testing out the landing return, and that is actually down in New York City, and your Kopernik membership would get you into that facility for free. So super opportunities to learn more and do it cheaply, and again, a Kopernik membership is actually quite a deal compared to some other. You look at some of the memberships costs for other museums. Kopernik is really quite the deal. Let's see. We do actually have a couple things here. Mike says fascinating history. He says I passed by the AP 101 shuttle lab many times. So Mike was one of our. Is actually a board member for Kopernik, but also was an engineer at Lockheed and IBM. And Denise asks, can engineers move around amongst the different industries, or is it somewhere they specialize in one area? Do you want to come back up and talk about that, David?
Very definitely. Well, I had quite an interesting career. We started out working on that IBSS system, and it was going to be one of many space programs. When I joined the IBM Space Guidance Center. That was at 8 o'clock in the morning. At 10 o'clock that very morning, they changed the name of the facility to the Electronic Systems Center, and all future space programs were going to be moved to Cape Canaveral, an IBM facility that was later closed, to Huntsville, Alabama, another facility that was closed eventually, to Houston, Texas, another facility that was closed, and to Westlake, California, another facility that was closed. So I was thankful that I chose to stay on in Owego and work on a variety of programs. There were a whole series of them that were extremely interesting. One of them that I particularly enjoyed was one called the Drone Formation Control System. And basically what we would do is we would take old jet aircraft, they would take out the ejection seat and put in a special control system that had hydraulic levers that would work the various steering commands to be able to control the aircraft in flight. And these were used for missions out at the White Sands Missile Range. They didn't necessarily want to always shoot the thing out of the sky. Sometimes you wanted to see how well these aircraft could perform evasive maneuvers against different weapon systems and so on. There was one mission where they were going to launch 2 aircraft, and the first aircraft got off all right. The second aircraft, the landing gear collapsed on the rollout, and it crashed, showering the runway with debris. The other aircraft was undamaged, and what they had to do is they had to put in a quick patch. Instead of bringing it back to that runway, they brought it back to a totally different runway with software that they already had in the system. There was another mission that they conducted that was way up range, where they had a huge mountain of explosive material, potassium nitrate, magnesium, gunpowder, petroleum oil, anything they could find. It was a huge thing, and what they were going to do was simulate a nuclear blast. And they flew 2 F-86 Sabre jets parallel to that blast to see what the concussions would be like as they flew through that. And all of this was way up range, where they had to have control of the aircraft through a series of relays, through a series of stations. Everything worked fine, and it was just an example of one of the many interesting programs. That program, interestingly, was put up for a bid, and what we call a Beltway bandit contractor submitted a lower bid and won the contract, and so IBM was no longer involved. And sometimes later, they came to IBM saying, you know, these people are really in trouble. Can you come and help us out? And the program manager, Dick Howell, told them, you couldn't print enough money to have us come back. In other words, it was a real slap in the face for all that we had done for them, and here they took the contract away from us. So it was a very interesting program. So to answer your question, I've had an opportunity to work on a number of different programs over the years, over my career, and I found it fascinating. I learned a great deal, and anyone considering engineering, no matter what the field, I'm sure you will find that you can get into programs that are incredibly interesting. I have an uncle who graduated from RPI with a degree in civil engineering, designing bridges and roads and so on. And one summer he worked at the U.S. Patent Office in Washington, and he decided to become a patent attorney. So he started out as a civil engineer building bridges and roads, and ended up as a patent attorney for American Optical. So you never really know where your career is going to take you, but with a good education, good solid background, you're going to find that you'll have a lot of opportunities and a lot of fun for the different things that come along in life. So by all means, work hard, get a good education, take advantage of every opportunity that you have, and who knows where life will take you. Thank you.
All right, actually, I'll chime in here in that, as I had mentioned, I was trained as an engineer, electrical engineer, and so when I first started working, I was a hardware engineer. I was actually designing the circuits, initially up in Rochester for Harris Corporation, and then I ended up moving to Boston, working for Wang Laboratories. Actually, was a competitor of IBM in the small computer space, designing disk drive controllers. As time went on, I moved into they started getting into networking, and so I moved into that group. Ultimately decided to get into system engineering, and they got my MBA, ended up moving to another company, and now I run an observatory. But what's actually great about moving around is that I think you end up bringing information that maybe some of the engineers who were sitting in a particular environment may not be familiar with. So having a different point of view of looking at a problem sometimes really ends up helping to solve the problem. So anyway, it's great again to have you here. We had a great crew here this evening. I put in the chat the link for our live computer session. David, did you have another thing you wanted to mention?
We've got a few moments. I was going to mention one additional item. I had indicated that I had worked on this drone formation control system out at White Sands, and we had taken old surplus Air Force jet aircraft. And what my job was to build a simulation model with all the aerodynamic characteristics of these aircraft so that we could rehearse a mission. In other words, we could issue the commands to an imaginary jet, and it would respond, increase thrust, bank right, climb, so on, so that we could rehearse a mission ahead of time to make sure that we understood everything that was going to happen and any problems that might occur and so on. And the first one that I started in on was a little one called a Firebee, which is just a little unmanned drone. And that particular mission, once it was completed, the jet would turn off and it would pop a parachute and it would land out in the desert, and the crew would go out and pick it up. And that particular one out at White Sands landed on a rattlesnake. So the guys brought the Firebee back, and they brought the dead rattlesnake with it, and nobody wanted it, so I snipped off the rattlesnake rattle tail and saved that as a souvenir, which I thought was quite interesting. Another one that I worked on was the F-100, and it was the first one that was capable of supersonic speed. And it had totally different aerodynamic qualities, supersonic versus subsonic. And we had to make sure that there was a smooth transition going through the Mach 1 phase. And that was kind of a difficult problem, and eventually I figured out a way to make it so that it would make a smooth transition going from one to the other. So working on Firebees and F-86s and F-100s and F-102s and so on. These were all very interesting things, and certainly not something that I had planned on when I initially hired into the company. But it's just an example of how life takes you on many, many different paths that can be very interesting, and only with a good education and firm foundation there do you have the opportunity to go on to these very different things. So again, reach for the stars, and who knows where life will take you.
All right. Well, thanks, David. Again, and thanks again for your presentation. Again, as an engineer, I always learn something new every time you come up. So, and I think of myself as a pretty geeky, space geek. So it's great to be learning something new. So what we're going to do is we're going to keep that link to get to the live observing session up. I'm going to actually sort of move into a thanks for viewing Slide. We'll keep that up for a couple of minutes, and then head on over, do a bio break, and get a chance to check out the close approach of Mars. So thanks again. Have a good evening. Wear your mask, and we'll see you in a couple of weeks at AstroFest.